We'll start in 2 minutes. Okay, we'll start. This is the third TA session of Structural Analysis 1 taught by Professor Amit Shah. Yes, good evening. Do you have a question? Do you have any questions from last class? Okay. Okay, so I am Trisha Chakraborty, one of the course teaching assistants. I am a PhD student at the Indian Institute of Science, Bangalore. We'll start with a brief recap of what we have looked at in the previous 2 weeks. In the first week, we saw there are four types of internal forces: bending moment, shear force, torsional moment, and axial force. And we have seen the common classification of elements, the idealization of elements like trusses, beam, truss element, beam element, and the common boundary conditions that we encounter in civil engineering structures like roller support, hinge support, fixed support, and so on. And we looked at structural indeterminacy, internal indeterminacy, external indeterminacy, and how it is calculated. A determinate structure is a structure that has just enough number of boundary conditions to maintain stability. If the degree of indeterminacy is in negative, that means the structure is not stable. It may undergo rigid body motion, it may undergo rotation, and if there are more number of constraints, that is more number of boundary conditions than required, it is an indeterminate system of degree 1, 2, 3, and the higher the degree of indeterminacy, the safer the structure is. So most structures that we see around us are actually highly indeterminate, but in this course, since this is an elementary course on structure analysis, we start with looking at determinate structures, since those are the ones that can be solved most easily by hand, just by mostly solving a system of linear equations, because we have three equations of equilibrium, and if we have three boundary conditions in the 2D plane, then we can solve all the reaction forces easily. And in the 3D plane, there will be six overall. So far, we have only looked at 2D structures, but if it is a 3D structure, there will be six modes of, like six equations of equilibrium, uh, linear displacement in this x direction, y direction, and z direction. There is three mutually perpendicular directions, and rotation about each of those axes. So there will be six uh, equilibrium equations, and to make a determinate structure in the 3D plane, we need six restraints. So maybe two fixed supports, because both the fixed supports will give three reactions each. And we looked at one of the most important topics in this course, the bending moment diagram and shear force diagram, how to draw them. In the previous week, week 2, we focused on trusses. This is one of the most this common in the common classification of elements. We saw truss elements. So in the previous week, we saw how to solve truss elements, what are the implications, and how to solve a truss, if a determinate truss, if the geometry and properties are given to you. And stability of trusses, and so, stability again has to do with determinacy, internal, external. And there were two special rules, that in a truss, all three support reactions cannot be collinear, and all three support reactions should not pass through a single point. In that case, the truss will not be stable. It will be determinate. It will be determinate, but it won't be stable. And we saw how to solve the member forces in a truss by two methods: method of sections, method of joints, and method of sections. Method of joints is where we go from joint to joint, and sections is when we cut the truss through a hypothetical section. And this one is the method of sections is useful when we are given to solve only one or two member forces in the middle of the truss, especially useful in competitive exams. And method of joints is something when we go from the joint to joint, we can solve the entire truss, and it generally takes more time. And today, this is week 3, so today we are going to look at the principle of virtual work, the unit load method to determine displacements in a truss. So this is basic. So last week, what we did was solving the member forces in a truss. There are in a structure, there are two types of responses. One are the force related responses, and the other is the displacement related response. So, for example, suppose imagine there's a beam, and we are loading it with a uniformly distributed load. What happens is, this is a transverse load. So in the beam there is a bending moment generated and a shear force generated. So that the bending moment and the shear force, they make a stress develop in the beam section. So that is the force or stress related response. But there is another kind of response. So suppose this is a beam and I'm loading it like this, then it will also, if I'm loading it like this, it will bend like this. So at the midpoint we will find some sort of displacement. It will bend in a profile like this, so every point will undergo some sort of displacement, unless of course if at the corner there is a hinge support or something, this point will not displace, this point will probably not displace, but the rest of the points will all undergo some sort of displacement. So similarly in a truss, what happens is, this is a beam example I gave. So that is a, so if it is a truss, since a truss element we know can only undergo tension or compressive forces, so the displacement will be an elongation or a compression. So that is the displacement at each node, and that will lead to a strain in the member. So stress and strain are two quantities you would have heard from earlier as well. So the stress related responses and the strain related responses are the two we are concerned about. And just for this sake of like future, in future you will study, when you go into design of structures you will see that there are two types of limit states according to which we design a structure. So one is the ultimate limit state or the collapse limit states. That means that if a limit state is basically an equation that must be satisfied for the structure to not fail. So that means for the ultimate limit states, they are related to the stresses. So that means that the stress developed in a structural element should not be more than its stress capacity. It will have a yield stress. So if the stress developed in the structure exceeds the yield stress, I will say that it has failed. So the ultimate limit state or the collapse limit state have an equation of the form that stress developed in the structure minus the yield stress should be less than zero, something like that. And then the other kind of limit states are the serviceability limit states, and they have to do with allowable displacements or the allowable deflection in a beam or in a column or any structural elements. And why they are important is because you like, basically, even if suppose a beam bends a lot, a beam bends like this, but it has not actually collapsed, it has not fallen, then my structure is fine, it is working. So technically, like, you can say that it has not failed. So why are we concerned about the displacements? We should only be concerned about the stress, because if the stress is exceeded, the structure will actually fall down. But why we are concerned about the displacements or deflections is that a structure has is built for a purpose, right? So imagine suppose in a factory we have an equipment, a large or a tall a crane maybe, that we have to pass through a door, and the beam on top of the door, which is called a lintel beam, suppose it exceeds a certain displacement, and in that case the movement of the crane is hampered. Then though the structure has not collapsed, it is not serving the purpose for it was built. Similarly, if in a residential building, if you see a beam has deflected a lot, if you just look at it, you will feel it is unsafe, and in that case the residents will want some sort of repair to make it better, because you will feel like it is going to collapse even if it is not actually collapsing. The psychological factor and all are also taken into account when we are designing as civil engineers, because after all we are serving the civil people, right? So all these are the serviceability criteria. So in our design codes, like IS 456 for concrete design, IS 800 for steel design, there are criteria mentioned that in each structural element, this is the maximum deflection that is allowed and all that. So the two types of responses are where I started this from is, since the two types of responses are the force responses and the displacement responses. In last class, what we saw was how to solve the member forces. We did not go into the displacements at all. We only saw how to find the force inside the truss, and by dividing that force by the cross sectional area, we will get the stress developed in the truss, be it tensile, be it compressive. And today we are going to look at how to determine the displacements in the truss. Yeah. So now this is a quick recap of what you must already have studied in class 8 or class 11 for sure. The work done by a force. How is work defined? In simple terms, work is force into displacement, as we think of it. When force basically it's force into displacement when the force and the displacement are in the same direction. Here, if it is basically in the algebraic in sorry integral term, it is integral fx dx. So dx is suppose I give a small displacement to this, like I apply a force on a point for a small differential displacement x dx. So the differential work done, that this should be like this fx dx is the differential work done dw, and to get entire work we have to integrate this or from the initial point to the final point. So if this is my initial state, this is my final state. So a is my initial state, b is my final state, and it goes through a zigzag path. Like it does not go through a straight path. Say at each point I have to look at the differential displacement and the force, and I have to take the this is actually f dot dx, so there should be a cos theta here. So the force into the differential displacement into the cos theta between the angles. So it is basically the component of the force that is acting in the direction of the displacement multiplied by the displacement itself. Conservative work is, this is a definition, when the work done is path independent. For example, gravity. So whether you drop a ball from first floor to the ground, or whether you take it by a S curve path, the work done will be the same. So that is a conservative force. And then there are non-conservative force that are work where the work is path dependent. For example, friction. So in friction, if you have 2 points on a floor, you take a body from A to B, and you take it on a longer path, the work done will be greater in the longer path, because friction is a non-conservative force. So this is the example. This is work done by gravity. This is, suppose this is a height h from which you drop a mass m onto the floor. So the work done is mgh. We know that because the force at any, the force on acting on the gravitational force acting on the body is always its weight mg, and multiplied by at, if you even if you do it in the integral form, you will see that whatever path you take, it is ultimately the vertical distance downwards that matters. So it will be mgh irrespective. And but if you are but friction depends. Once the frictional force does not work like that. It will depend on the path. So that it will depend on the path we are taking it along. At equilibrium, a structure deforms such that its potential energy is minimized. So this is a definition kind of thing that has been found to be true. A structure deforms such that its potential energy is minimized. Now let us look at this term deformation once. What is deformation? Deformation is a change from initial configuration. So, deformation is any sort of change from the initial configuration of a body. So, now a deformation only occurs when there has been some sort of resistance against it, or some force acting, not just a force acting on it. Suppose you drop a ball from the first floor, till the time it is falling in the air, assuming there is no air resistance, still the time it is falling down, no one is stopping it, no one is resisting it, so there is no deformation. But when it falls on down on the ground will apply a reaction force on the upward direction. That is when the ball deforms. So and this law says that the structure will deform in such a manner that its potential energy will be minimized, and external loads will be equal to the internal forces. So, and I mean all the external loads, it can be in all sorts, all different directions. There can be moments. So loads or forces, we say force, but we actually mean force and moment both in this bracket. Okay, so all the resultant of the external forces, loads, moments, everything acting on the body will be equal to the resultant of the internal forces, and the external work will be equal to the internal work. Principle of virtual work. This is the topic of today. Work done by a real force acting through a virtual displacement, or work or virtual or a virtual force acting through a real displacement. So this the work done by these two are called is called virtual work. So suppose you have a spring mass system. This is a very common system that is often studied. This is a mass m. So you know that the downward force acting on it is the weight mg. So the spring has to deform in such a manner so that the resistance force developed inside the spring is mg. So if it is to be in equilibrium, so we know how that is done. The spring force is k into displacement. So if delta is the displacement of the spring, k into delta is equal to mg. So that is how we can get the force. Sorry, that is how we can get the displacement that the spring has undergone to reach equilibrium. Now suppose I pull down the mass by a, I have actually not actually pulled it down, but if just imagining that it has been pulled down by a distance of delta star, this is called a virtual displacement. The principle of virtual work is, in equilibrium the virtual work of the forces applied to a system is zero. So the total virtual work applied to a system is zero. We'll get to the implications of this in a minute. So if you want to solve this displacement, which I said earlier in a different manner, here mg into delta star is the virtual work done. And if suppose I don't know what that f equal to mg, it is obvious to us that f should be equal to mg, but suppose we don't know that and we are just going by the principle of virtual work. The virtual work done is mg into delta star, and the real work done, one second, I think it should be mg delta star minus f delta star. That is the virtual work done, because mg is to acting downwards, f is acting upwards. So the virtual work done by mg is positive mg into delta star, because delta star is also in the downward direction and mg is also acting in the downward direction. And while f is acting in the upward direction, delta star is in the downward direction. So it will be mg delta star minus f delta star. That is the net virtual work done on the body, equal to 0. From that we get that f equal to mg. This seems a very intuitive answer, which is, of course we can see this, but it has a lot of implications in a lot of complex problems. So virtual work helps us solve those easily. Application of principle of virtual work: the unit load method to find deflection of stresses. Yeah. The unit load method to find deflection of stresses. This is one of the applications. The response of a structure, as I said, has two categories: forces or stresses, the collapse limit state, and displacements or strain, the serviceability limit states. And in a truss, there are two kinds of forces we are concerned with: the member forces and the nodal displacement. So the member forces that we have already seen how to solve by method of sections, method of joints, and the nodal displacements are something we are going to look at today by the unit load method. This method is a technique to quantify displacements or and rotations of equilibrium configuration of a structure, that is the shape of the structure after it has managed to equilibrate the applied loads. So as I said, a structure does not deform till it has some loads acting on it as well as some sort of resistance. So till it reaches equilibrium, there is no like till it reaches an equilibrium state, there is no deformation. So suppose there is a beam. I always give the beam example because it is the most easily visualizable. But today we're looking at a truss, but still in a beam. As I said, that if a beam has a uniformly distributed load, it will deform and with like hinge support at both ends. Yeah, let's say one hinge, one roller, it will deform in a shape like this. So the technique to quantify displacement and rotation of each point. The rotation is a little harder to imagine. So suppose this is my beam. It has deformed like this. So the rotation, every point you can see it was originally, it was a straight line like this, then it became something like this. So the displacement, you can easily imagine that downwards, all the point are going downwards a little bit, but if they are actually also rotating. The point was initially, one point was like this, it rotated some amount to give the deflected shape, so that a little bit of an element is now oriented like this. So a differential element on the original beam is deflected at this, on this side it's deflected like this. So these are the rotations going on. So if it's a symmetric simply supported beam, then with the downward loading, then one half of the beam will undergo clockwise rotation, the other half will undergo anti-clockwise rotation. So the displacements and rotations, as I said, when we say force, we don't just mean linear force, we also mean the moments with it. So when we talk about displacements, we automatically also include the rotations in it. So due to a force we get a displacement, due to a moment we get a rotation, and they are just complementary quantities, and both we are interested in both of them. So, the unit load method is a technique to quantify displacements and rotation of equilibrium configuration of a structure. That is the shape of the structure after it has managed to equilibrate the applied loads. Virtual unit force is applied at the node where we want to calculate displacement. So, I'm given a truss. I ask you that find out the displacement at this node. So in a truss, we know that since rotation is not relevant in a truss, because in a truss there is only axial force. So at each node we have only two equations of equilibrium, sigma fx equal to 0 and sigma fy equal to 0. So the two types of displacements at the node will be something in the x direction, something in the y direction. And I mentioned this before as well. It does not actually mean x direction and y direction the way we imagine. It might not be, you might not find the answer in the horizontal direction and in the vertical direction. You can choose any two mutually perpendicular directions and tell me the displacements in those two directions. And we know that this, the sum of square root method, that if the displacement in x direction is delta, in any direction is delta x, and the perpendicular direction is delta y, then the net displacement will be delta x square plus delta y square and root of that. So that will be the net displacement. But in the in this method we will find out that both the modes of displacement separately. So if I ask you to find out the displacement in the x direction at a particular node, you will apply a virtual unit force along that direction at that node. And analogically, a virtual unit moment, this is not applicable to truss, I think, but in beams the unit load method is not actually not just restricted to finding displacements in trusses, it's applicable for all structures. Analogically, if I ask you to find out the slope or the rotation at a particular point, you will apply a virtual unit moment at that point to get it. And for a unit force, the external virtual work done will be 1 into delta, and this delta is the unknown thing, this delta is what we don't know. And since external virtual work is internal virtual work, delta will be equal to the internal virtual work. So the steps, let's look at the steps. This is a very simple determinate truss. It has a hinge support here, a roller support here, so it is determinate because it has only three support reactions and three equations of equilibrium. Now at step 1, due to given load system, we will calculate the forces in all the members P1, P2 up to Pn, let's say. So there are n members, and the W1, W2, W3 are just like representatives. It can be, the loading can be of any combination. So this is the real loading condition is the W system of loading. For that I am going to solve the entire truss. So this process is a little long because you have to solve the entire truss. So it's better to go by method of joints. I generally go by method of joints when I have to solve the forces of all the members. So let us say that this is the P system of forces, and then what we will do is we will forget about all the external loads, we will remove all of them, draw the truss without any of the forces on it. And now suppose whichever point, suppose I asked you, give me the downward displacement of node E, then what I'll do is, when you have drawn just the truss again with the boundary conditions will remain the same, but the forces will be removed, and I will just put a one unit load in the downward direction at node E. and this one will be of the unit will be generally of kilonewton, because these w1 w2 w3 will generally be given in kilonewton. So whatever be the unit here, you'll put a 1, that unit force, in the direction, by the direction I don't mean downwards or upwards, I mean whether in the downward direction, or like in the vertical direction, or the horizontal direction, or any random direction. I can ask you, give me the displacement in along this axis. In that case, you have to apply an inclined load here. So that you will do, and then you will again solve the entire truss, and so remove all given external loading, apply a unit load at C. Suppose I'm given C in the direction of desired deflection. If I'm given at C, due to unit load alone, find the forces in all the members, say K1, K2 up to Kn. So this is my K system of forces. So now I have the forces in each member for the original loading conditions, and I have the forces in each member for this unit loading condition. And also you keep the signs here, the positive for tension, negative for compression, or vice versa. You solve the entire both the systems with the same sign convention, and write down the system of forces with sign. So the deflection at joint C in the direction of the applied unit load is given by sigma pkl by ae. So it is generally done in the form of a table like this. So I'll make one row for each member. I'll make one column for the P forces, column for the K forces, one column for the lengths. So you can this generally we are given the vertical and the horizontal lengths, and the inclined lengths you can solve by Pythagoras theorem. And I will multiply these three entries of each row, write this down, and then I'm going to add all the elements of this column to get the sigma pkl, and then I'm going to divide it by AE. A is the area, cross section area. E is the Young's modulus, and generally the all the cross sectional areas will be given the same when you are asked to calculate. But if it is different, then the sigma has to be in a like in a broader bracket. The entire thing. Suppose the area and the Young's modulus also vary for each of the members. Then in this, I'll make two additional columns here, A and E, and then I'll calculate this whole quantity pKl by AE for each of the members, and then add it all. So if D comes out to be positive, uh, the deflection of joint C will be in the direction of unit load. Not D, this will be sigma C. If this delta comes out to be positive, then the displacement or the deflection at the point will be in the direction I had assumed. I have put, when I put the unit load, I put it in a certain direction, right? If I put the unit load in the downward direction, and then when I end up with this quantity that is positive, the interpretation is that the deflection was actually in the downward direction. And if I put a downward unit load and I got a negative quantity as my answer, it meant that the node was actually displaced upwards. So that is how I'm going to interpret and write it when I'm asked to find the deflection in this point. I'm going to write this amount normally in millimeters, downwards or upwards, or towards the left, towards the right. Now let us look at examples. Yeah. So this is a truss with a hinge here and a hinge here. It has two members. And see, we initially remember when we were looking at stability of trusses, we had seen one criteria, that a truss should always form, I mean, the minimum rectangles should be formed. So, sorry, triangles. A truss must form triangles with its members. So, you can say that this does not actually form a triangle because it is just two members here. But see, since these are both hinge supports, it is almost as if there was a hypothetical member here, because a member here means it means an inextensible member was here that cannot like of infinite rigidity. So suppose there was a member here, it is never going to elongate or compress because both its ends are fixed. So this is a valid truss even though it does not form a triangle, because this could be a hypothetical member here. So uh, there is a P force. This is the original system is a P force is applied in the downward direction at joint C. So the P system of forces, we consider the joint C. Here P is downwards, FCA, FCB, as we have seen in the last class. To solve it, we first conserve the forces along the x-axis. So we get minus PCA. It has a cos 30 degree. Since this is a symmetrical truss, you can see that each of these members are inclined at 30 degree from the horizontal. CA is in the upward direction, CB is down. So minus PCA cos 30 degree minus PCB cos 30 degree is 0. So we get PCA is equal to minus PCB. And when we are doing the sigma Fy, when we are equating all the forces to 0 along the y direction, we get PCA has a sine 30 component upwards, because as we saw last time, we are just assuming the forces away from the joint. We are assuming it to be tension, so we are assuming the arrows pointing away from the joints. So this force along this direction has an upward component in which is PCA sine 30 degree. And the downward things are, there's one this load P acting in the downward direction, and PCB sine 30 degree acting downward. So both these are minus. From these two we solve that PCA is plus P, so tension, and PCB is under compression of P. Now the K system of forces, I am asked to find. I'm basically asked to find the displacement at this joint C in the vertical direction. So I'm going to apply a unit load here, and then we solve this. Since this is a linear system, because only one load is applied. These you will start to understand intuitively later on, that in this system, once we have solved PCA is P and PCB is minus P, if I replace the P, I remove the P and put a unit load there, the forces in each of the members will just be divided by a factor of P. So PCA here will be KCA will be plus 1 kilonewton, KCB will be minus 1 kilonewton. But if you are not comfortable with this, just solve it again. Just solve it with the method of joints again, with remove this P and put a 1 in the downward direction here. So you will get this answer. And then to find the deflection at C, I am going to find, let's see the length. Length is L here and here. So for this CA member, P is P, K is 1, and L is L. So it is PL. And for the CB member, the K is minus 1, P is minus P, and the length is L. So we get 2PL by AE. So this is the deflection. And just for the sake of unit, just check once about the unit. Is P is 4, so it is kilonewton. Length is meter. Let's say, okay, meter, kilonewton meter. And in the denominator we have area, that is meter square, and the Young's modulus is kilonewton per meter square. So yes, the kilometer crosses out, meter square crosses out, and we are left with a meter and or a millimeter, whatever. See, when you are actually given numerical values, this was just in algebraic terms. If you are given numerical values, just be careful. Put all these units in a consistent manner. So if you are putting the length in meters, make sure that you convert the area in meters as well, and make sure the Young's modulus is also in kilonewton per meter square. But generally, the Young's modulus is given in megapascal units. So megapascal is Newton per millimeter square. So be careful about the units. You must, in any formula, you must of course put all the units in the same, say, in a consistent manner. So all the forces should either be kilonewton or Newton, and all the displacement should be either meter or millimeter. Do not mix them up. Then you are going to come up with the same, like the value will be the same, but it will be by multiplied by some factor of 10, this side or that side. And in competitive exams like GATE, they will make sure to give those closely spaced answers. So if the actual displacement is 2.3 millimeter, they will also give 0.23 as an option to fool you. So be very careful about that. This is another example. This is Okay, one thing I have to mention, that last day I said that in solving any trust, the first step is solving the boundary conditions. Generally, it is so, but this is a special, like a very small trust. So here you will see that we solved the both the member forces without even going into the support reactions. So there is no general rule, basically, that there are approaches, but the more you practice, you will know how to fastest approach the problem, which is again very useful in the competitive exams, because they are a race against time. This is a triangular truss with a roller support here, a hinge support here, and three members. So I start by solving the support reactions. There are three. There is one in the upward direction at this point P, and there are two, one in the upward direction, one one in and one in the vertical direction, one in the horizontal direction at the hinge support. So I have three equations of equilibrium. One is sigma fx equal to 0. This is there is one load here 135, and one horizontal load, horizontal reaction here hr. I've assumed it is towards the left, so hr minus 135 is 0. So the horizontal reaction is obviously 135 in the left direction. And another equation uh, is conserving the moment. As I say, when we write this moment equation, we try to choose the point through which I have the most number of forces passing, so that they will not show up in this equation. So I am taking the moment about r. What are the forces that are providing a moment about r? One is this rp, one is this 135, and this rr and hr do not give any moment because they pass through the point r. So rp into 4.5 is a clockwise moment. 135 into 6 is also a clockwise moment. So we are writing both these as plus, and we get rp is 1 minus 180 kilonewton in the downward direction. And if when we write sigma fy equal to 0, we'll see that rp plus rr should be equal to 0. So they are basically equal and opposite forces. So rp is minus 180 towards downwards, and rr is plus 180 in the upward direction. So when we are solving the truss, we have to solve the entire truss. So this is so we are let's say we are going by joint r first. This is joint r. We have 180 in the upward direction and 135 in the left direction. So this is 180, this is 135. PRQ and PRP, we have assumed both of them as tension. So away from the joints, we write down the two equations simply. Sigma fx is 0, so from that we get PRP is minus 135. So it is under compressive force. And from sigma fy equal to 0, we get PRQ equal to minus 180. So this is also a compressive force. This is one of the best sort of joints we can find where there is no inclined member. So we can just directly, there is no need to take the sine or cos components. We just directly get the forces. At joint P, let's see, at P we have 180 acting down the downward direction and two members here. So 180 in the downward direction, PPR, PPQ here, and there is this angle theta. We have to find out this theta. You know that tan theta is 6 by 4.5 here. So from once we know the tan theta, we can get the cos and sine. The formula sigma Fy equal to 0 is PPQ sine theta acting in the upward direction is equal to 180 in the downward direction. So PPQ is 225 kilonewton, and PPR we have already solved earlier. So we know it is 135 kilonewton compression, because PRP we are writing PRP here and PPR here, but they are the same force, because in a member, whether you solve from this joint or that joint, you are going to get the same answer. You are going to get the same answer, and you're going to get the same interpretation of tension or compression. So even if you solve PR from here, you will get 135 in compression. And the K system of forces, mm, I think, wait. Yeah. So the displacement that has been asked is the horizontal displacement in this point Q. So all the member forces will just be, since there is only one force acting here, 135. All the forces acting, if you remove the 135 and replace this by a 1, then all the forces will just be divided by 135. This method will not act if there are multiple forces. Okay, this directly dividing method is just acting when there is only one force and it is just getting divided by a value. So P by 135 for each member. So PQ, QR, RP, this is tension, these two are compression. And if we solve K, we will get a tension, and the sign remains the same. We'll get these values. And length, this is 4.5, this is 6. So this will be 6 square plus 4.5 square, the root of that, which is 7.5 apparently. So we get this, the sigma pkl is this, and you divide by the area and the Young's modulus, and you get something like this. So this is a like this these were simple problems. This is a little complicated, but remember about the zero force members. You straight away identify the zero force members, and you see this simplifies. It goes this simple. Like there are so many members. This looks like such a complicated truss. You have to solve so many joints to get the entire system. But basically, uh, what were the rules of zero force members? That if there is the, like, at a point there are three members, two of them are collinear and one is not, and at that point there is no applied load and there is no boundary condition, then the non-collinear member will have no force, so it will be a zero force member. We can remove it from the diagram. One second. So this member, you start from here, these two are collinear, this is not, so this member does not exist. Remove this, then this member will not exist because these two are collinear, this is not. Then from this side this will not exist, then this will not exist, and since these two don't exist, this will also not exist, like that. And then when all of these don't exist, even this will not exist, like that. If you start drawing and removing one of the members, you will see it just simplifies to a literal triangle. It is evident from the diagram that all the interior members will carry zero forces. So the P system of forces, if you solve, you can solve the support reactions, and by this, from this you will get P by root 2, P by root 2, and here P by 2. This will be compression, this is tension, I think. And the K system of forces, if you are asked to find out the downward displacement at this point, it will be divided by P. Now note one thing, it is not necessary that since I have put a force, since in this truss the loading condition is a horizontal force, it is not necessary that even the displacement will be asked at the same point in the same direction. I could also ask the vertical displacement at Q. I could also ask the horizontal displacement at P, because this is a roller support. It is free to displace in the horizontal direction. So in that case, the P system of forces will be this, and the K system of forces will be solved by applying horizontal force at P. In that case, you can of course not divide this by P by 135 because the loading conditions are different. Then you have to actually solve the truss again. But if your deflection is asked at the same point where the load is in the same direction and there are no other forces on the truss, that in that case you can just divide the, in the K system of forces, you can just divide it by the magnitude of that force. So the assuming tensile forces are positive and compressive forces are negative, the deflection at C will be uh, sigma pkl by ae, just like we did before. Determine the horizontal displacement of roller support. So this is one of those questions where the applied load is here, but the displacement is asked at some other point. Determine the horizontal displacement of roller support of the truss. The cross section of each member is 3000 millimeter square. Take E equal to 200 kilonewton per millimeter square. So this is consistent with units. The forces are also in kilonewton, and these are also given in kilonewton and millimeter square. And but the length also, make sure to put them as millimeter because it is given as meter here. So let's start by solving the support reactions. There are two forces here, 100 here at F and 300 here at C. This is a hinge support, this is a roller support. So I assume RA and HA and RB here. So sigma Fx equal to 0. From that, we'll get HA equal to 100 because there are just two horizontal forces in the system. Sigma Fy equal to 0, we'll get RA plus RB is 300, and sigma MB equal to 0. When we are taking the moment about this HA is passing through the line B, so it will not have any component of moment, and the RB is passing through B, so it will not have, but RA into 9, because see 3 3 3, so RA into 9 is a clockwise moment. 100 into 4, this vertical 4 is also a clockwise moment, and this 300 is providing an anti-clockwise moment. 300 into 3, so it is minus here. From that we get RA as 55.55 and RB as 244.45. So we have solved the support reactions. Now I want to solve the forces at and each of the members. So I have to go joint by joint because there are no zero force members. Okay, so this is a zero force member, this you can remove, but apart from that there are a lot of members we have to solve. So we are starting from joint F at this since this one second. Sorry, not a joint F. Joint F has so many members at it. So we are starting at joint A here. This is one member, this is one member, because in method of joints we can only solve joints which have two uh, two unknown member forces, because we have only two reactions at two equations at each joint, sigma fx equal to 0 and sigma fy equal to 0. So here we know that there is an upward reaction of 55.55 here, a horizontal reaction of 100 kilonewton here, and I have two members, AF and AD. So PAF in the vertical direction has a sine theta component, plus 55 is 0. So PAF is minus 69 compression. So this member is under compression, and in the horizontal direction I have PAD, I have PAF cos theta, and 100 is on the other side. So PAF cos theta plus PAD is 100. So from that we solve PAD is under tension. Then I move on to, now I have these two, I move on to the joint D. At D, we know that this, we can directly see this is a zero force member. So PAD and PDC must be equal. PAD we have already solved. So PDC is also 144.66 kilonewton tension. Then we move on to joint F. Now that we have solved these, we have only two unknowns. Similarly, like here at F, we know this is 0, so PFE and PFC are the only unknowns. So we solve them, we get PFC as a tension, PFEF as a compression. At joint B, the other support, we have two unknowns and there is one reaction. It was a roller support, so we have one reaction here. From that we get these two, and finally at joint F we have one force left, this PEC, and from that we get that. And the K system of forces, now we have been asked to find the horizontal displacement of the roller support. So this is my roller support. I have to take a unit load at B in the horizontal direction. Whether you take it to the right, whether you take it to the left is up to you. If I take towards the right and you take towards the left, we are going to end up with the final solution, we are going to end up with different signs, so we will interpret around that. If I take towards the right and I get a positive value, that means that I had assumed the correct direction, so it has actually displaced towards the right. In that case, you will get a negative value and you will interpret in the same manner. So of course the sign convention and all is made by us, and we can change it according to the people who are giving it, but the interpretation must be the same, no, right? The ultimate displacement of a certain point in a truss has to be the same whichever sun convention you calculate it with. So just like whatever unit you use, if I am working in the meter system and you are working in the millimeter system, if the displacement is 1 millimeter, if you will get 1, I will of course get 0.001. The ultimate answer has to be consistent whatever conventions you are using. So I remove all the external loads and I put a 1 kilonewton in the left direction here. And then when I am solving the support reactions, I'll see that this HA will be 1, because HA will be 1 because I'll just solve, I don't have any other horizontal force, so these will be 1. And there will be no reactions here, I think. There will be no, we'll find out that the RA and RB will be 0 in the vertical direction. So when I'm solving the K system of forces, this is interesting because this is a zero force member. When this, wait, how are all these? We have to solve this. Like, this is what will ultimately being got, that AD, DC, and CB. These three members will have 1 kilonewton tension each, and all the others will be zero force members. Oh, basically because since there are no vertical force here, so since at this point the vertical reaction is zero, when we are doing sigma Fy equal to 0, we will see that this has no force, because if this is carrying any force, then who will balance out the vertical component of it? So this will be zero force, this will be zero force. From that we can, if we solve it, it will find it fast enough that all none of these carry any forces, and each of these members, the base members, have 1 kilonewton tension each. So this is, so here we actually draw the table. In the previous questions there were only two or three members, so you were adding by hand, but here there are so many members. So write down all the p's with sign, write down all the k, all the lengths, and find out the pkl, and then divide by the a and e. Pkl we are getting, kl was in, this is in meter. So I think these also have to be converted into meter, otherwise, right. A is given in millimeter square and 200. Okay, we did not need to calculate, because when I'm multiplying the a with the e, the millimeter square is getting cancelled anyway. So I'm getting the final answer in meter, because the only meter that remains is the length of this, and then we multiply it by 10 to the power 3 to get the millimeter. So this 10 to the power 3 is to get the answer in millimeter. So this is how it's done. So we come to the end of this class. This was a simple enough topic. Are there any questions? Those of you who don't have any questions may leave. If you have a question, you can ask. I'll wait for a few more minutes.
Ma'am, if the temperature stresses is included, so how can we solve that problem?
Okay. If the temperature stresses are included in, can do you have a problem to? I need to see how, what is the input given in the problem. Do you have any problem?
Yes, ma'am. Please give me 5 minutes.
Yes, yes, sure. You can share the screen if you like.
Ma'am, actually, I don't have the problem on my screen, but I will read it.
Okay, read it.
Okay. The member of the frame, which is as shown in the figure, having the cross-section area of 10 centimeters square, if there is a rise in temperature of a member AD by 30 degrees Celsius, determine the forces due to the change in temperature, given that the coefficient of thermal expansion is 12 into 10 raised to the power minus 6 and E is equal to 205 GPa.
Okay. Okay. So what one second. Let me just think. So what happens when there is a temperature stress is, we know the formula of the, you know the formula of the stress developed in it, right? What was the formula? Wait. I think something into alpha into delta L. Wait. What was the formula? Do you have the formula, or I'll check? Stretch.
And that is the formula, that is alpha TL
Yes.
divided by summation of k square L upon AE.
Forget the k square L about A so far. For initially, just first think that the alpha into delta T. One second, one second. I'll just give me 2 minutes. So the third, can you see my screen?
Yes, ma'am.
So this is the formula of thermal stress. General thermal stress is Young's modulus into expansion of coefficient of thermal expansion into the difference in temperature. So that is the stress developed in that, in a particular member. So what kind of structure is given? It's a truss structure.
Yes, ma'am. It's a cantilever truss.
Okay. So what I think is that there will be one second. I'll just need to think about it a bit. 1 second. Give me 2 minutes, okay? Okay, I have to, like, to explain it. I have to write it and show. I will, like. Can you give me your mail ID? I will solve a problem and send it to your mail
Yes,
ID
ma'am.
tonight. Because I don't have it solved right now. I don't have a pad to write on, like a tab or something.
Okay, ma'am.
You can write in the chat box. Okay. Okay, thank you. Any other questions from anyone?
मैम,
यस।
मैम एक क्वेश्चन है, आपको मेल पे भेज दे रहे हैं, आप थोड़ा देख लीजिए ना।
अच्छा, अभी तक आया नहीं है, फिर से सेंट दिखा रहा है क्या तुम्हें?
वो मैम वैसे भेज रहा हूँ बट अटैचमेंट नहीं हो पाया।
अच्छा, 2 मिनट वेट कर। स्क्रीन शेयर, विल यू ट्राई शेयरिंग योर स्क्रीन?
मैम मैंने शेयर कर दिया।
हाँ हाँ हाँ, आया 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 है। व्हाट इज द रोटेशन? सी। हाँ, तो इसमें क्या करना है कि पहले आई द कॉन्सेप्ट। ओके, दिस इज अ फ्रेम, सो फ्रेम का भी के ऊपर भी यूनिट लोड मेथड अप्लाई कर सकते हो। तो द ओरिजिनल सिस्टम इज वेयर देर इज वन मोमेंट हियर, सो यू कैन सॉल्व दीज टू मेंबर्स एंड देन आई थिंक यहाँ पे एक यूनिट रोटेशन, एक यूनिट मोमेंट, इस एम को हटा के यहाँ पे एक यूनिट रोटेशन, यूनिट मोमेंट 1 किलो न्यूटन मीटर देके इसको सॉल्व करके होगा क्या? I mean, about the frame, I have to, since we have just gone up to trusses right now, but I think the concept will be the same, कि जिस पॉइंट पे रोटेशन मांगा है उस पॉइंट पे मुझे एक यूनिट मोमेंट देना है एंड देन आई हैव टू सॉल्व द केस सिस्टम। Did you approach it that way and see if you're getting the proper answer?
I try, ma'am.
Your
Ma'am,
voice
I,
is clear.
okay,
Yes.
ma'am,
What?
ma'am.
तुम्हारा वॉइस एकदम क्लियर नहीं आ रहा है. यू कैन राइट इन द चैट बॉक्स.
Okay. मैम एफईएम जीरो आ रहा है मैम, इसमें कोई स्पैम लोडिंग नहीं होगा मैम. दिस इज करेक्ट.
फिर से बोलो. क्या व्हाट इज करेक्ट?
एफईएम है ना, वो जीरो आ रहा है मैम, कोई इसमें स्पैम लोडिंग नहीं होगा मैम. दे
पैन लोडिंग. मुझे एक बार फ्रेम्स 1 सेकंड. यूनिट लोड मेथड फॉर फ्रेम्स.
मैम बीसी का स्लोप डिफ्लेक्शन मैंने, तो
हाँ हाँ.
मैम.
अच्छा, तुमने स्लोप डिफ्लेक्शन मेथड से किया है ये?
हाँ जी.
अच्छा हाँ. तो फिर बोलो फिर. प्रॉब्लम कहाँ पे है?
और मैम निकाला उसके बाद.
तुम्हारा वॉइस एकदम क्लियर नहीं आ रहा. मतलब बीच बीच में कट रहा है. चैट बॉक्स में लिख सकते हो.
मैम आई गॉट द आंसर.
Okay, okay, you got it. Slope deflection methods or moment rotation should give the answer here. I thought you're asking from the unit load method.
मैम
हाँ.
और मैंने को इसके पहले क्लास में भी क्वेश्चंस दिया था, तो आपने बोला था मैम कि मैं बाद में बताऊंगी.
हाँ मतलब मैं अभी तक फ्रेम वो भी फ्रेम का क्वेश्चन था ना. तो वो फ्रेम वी आर गोइंग इनटू फ्रेम्स इन अ फ्यू वीक्स लेटर. सो आई थिंक फ्रॉम वीक 6 or 7 उस टाइम पे. आई थिंक. वेट. लेट मी सी द क्वेश्चन अगेन. I mean, I don't have it documented with me basically properly. ये वाला ना.
यस मैम. करेक्ट. मैंने ट्राई किया, मेरे से नहीं हुआ मैम, फिर मैंने इसको छोड़ ही दिया. अब इसको सॉल्व ही नहीं कर रहा हूँ.
अच्छा. सुनो. So firstly, you know how to solve indeterminate structures.
यस मैम.
You know how to solve indeterminate structures, like you know how to solve the support reactions here.
मैम नॉट इन. मैम पूरे अच्छे तरीके से तो मैम मैं नहीं कर पाता हूँ, मुझे हेल्प चाहिए रहता है मैम. कैलकुलेशन करने में प्रॉब्लम होती है, तो मैं पूछ लेता हूँ.
पर उसका मेथड्स है ना. मतलब टू सॉल्व एन इंडिटरमिनेट स्ट्रक्चर्स देर आर सम मेथड्स where you use the E and I, the Young's modulus and the moment of inertia, and there are some methods. So to solve this problem, अगर एक बेंडिंग मोमेंट डायग्राम मुझे एक इंडिटरमिनेट स्ट्रक्चर का करना है, चाहे वो फ्रेम हो बीम हो, द फर्स्ट स्टेप इज इंडिटरमिनेट स्ट्रक्चर का रिएक्शंस कैसे सॉल्व करना है पता होना चाहिए. तो दैट टॉपिक वी आर मूविंग इनटू फ्यू वीक्स लेटर. Wait, let me see. So week 7, 8, 9, we see how to solve the. We are going to look at how to solve the इंडिटरमिनेट स्ट्रक्चर्स एंड आफ्टर दैट अगर तुम्हें इंडिटरमिनेट स्ट्रक्चर अगर तुम्हें इसका तीन यहाँ पे तीन फोर्सेस होंगे रिएक्शन वन इन द वर्टिकल डायरेक्शन वन इन द हॉरिजॉन्टल डायरेक्शन वन मोमेंट वो हो गया तो फिर बेंडिंग मोमेंट डायग्राम यू विल ड्रॉ इन द सेम मैनर एज वी डिड अर्लियर यहाँ पे सपोज एक मोमेंट आया तो यहाँ पे जो मोमेंट आएगा यहाँ पे एक पॉइंट मार्क करना है एंड यहाँ पे कुछ मोमेंट आएगा यहाँ पे मार्क करना है एंड देन एट दिस देन यू आर गोइंग टू वॉक फ्रॉम वन साइड जैसे हम कर रहे थे यहाँ से यहाँ तक जाने के बाद इस पॉइंट पे मोमेंट निकालना है जब तुम इस साइड से आ रहे हो on the only forces that will matter is this and this and these will not matter ये सब साइड में जो है वो नहीं होगा तो बी पॉइंट में मुझे कोई मोमेंट मिलेगा एंड सिमिलरली उधर फिर जाने के बाद सी पे कुछ मिलेगा एंड देन जैसे हमने बीम के लिए किए हैं इफ देर इज नो लोडिंग इन दिस जोन द बेंडिंग मोमेंट डायग्राम विल बी अ स्ट्रेट लाइन सो ए पे जो भी मोमेंट है और बी पे जो भी मोमेंट है उसको स्ट्रेट लाइन से ज्वाइन करना है और डी और सी को भी स्ट्रेट लाइन से ज्वाइन करना है और बी और सी को एक पैराबोलिक लाइन से ज्वाइन करना है बिकॉज एक यूनिफॉर्मली डिस्ट्रीब्यूटेड लोड इसके ऊपर है तो बेसिकली ये यहाँ पे तीन फोर्स है मतलब दो फोर्स एक मोमेंट यहाँ के दो फोर्स एक मोमेंट वो सॉल्व हो गया उसके बाद बेंडिंग मोमेंट डायग्राम कैसे ड्रॉ करना है वो समझ आया है
मैम आपने क्या बोला डी और सी को पैरेलली लाइन से ज्वाइन करना है?
नहीं नहीं डी पे मोमेंट सपोज मेरा 10 आ रहा है और सी पे सपोज 5 आ रहा है इन द सेम सेंस इन सपोज डी पे आ रहा है क्लॉकवाइज 10 सी पे आ रहा है क्लॉकवाइज 5 तो फिर स्ट्रेट लाइन से ज्वाइन करना है यहाँ पे मुझे एक 10 या इसको एक एक्सिस मानो यहाँ पे एक 10 पॉइंट ड्रॉ करो यहाँ पे एक 5 करो और ऐसे एक स्ट्रेट लाइन से ज्वाइन करना है लाइक दिस और अगर इस पे प्रॉब्लम हो रहा है तो यू कैन जस्ट ड्रॉ सी डी एज अ हॉरिजेंटल मेंबर सेपरेटली मतलब अगर तुम्हें इसी फ्रेम पे ड्रॉ करने में प्रॉब्लम हो रहा है ए बी बी सी और सी डी को अलग अलग स्ट्रेट लाइन ड्रॉ कर लो एंड देन जस्ट शो दैट पार्ट कि डी पे जो भी मोमेंट है सी पे जो भी मोमेंट है स्ट्रेट लाइन से ज्वाइन होगा क्योंकि देर इज नो फोर्स इन बिटवीन दिस लाइक इन दिस जोन देर इज नो फोर्स
ये मैं ट्राई करता हूँ मैम।
हाँ पर उसके पहले इंडिटरमिनेट स्ट्रक्चर को सॉल्व करना पड़ेगा ये कंसिस्टेंट मेथड ऑफ कंसिस्टेंट डिफॉर्मेशंस ये जो मेथड्स है ना टू सॉल्व इंडिटरमिनेट स्ट्रक्चर इन सब से किसी एक से सॉल्व पहले करना पड़ेगा उसके बाद आएगा डायग्राम बेंडिंग मोमेंट shear force डायग्राम का फर्स्ट स्टेप तो ऑलवेज इज सॉल्व द सपोर्ट रिएक्शंस तुम लोगों के पास एक बात बोलो तुम्हारे पास गूगल ड्राइव का एक्सेस है क्या जहाँ पे स्लाइड्स अपलोड होता है
क्या मैम?
you guys have access to the Google Drive link where the slides are being uploaded of the TA sessions? ये
नो मैम।
PowerPoint presentations? हाँ
मैम मैम उसका एक्सेस हम लोग के पास नहीं होगा।
नहीं वो
एनपीटीएल एनपीटीएल के लिए की बोल रही है ना मैम?
हाँ 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 हाँ
नहीं मैम उसका एक्सेस हम लोग के पास नहीं है उसका एक्सेस सिर्फ आपके पास होगा मैम।
अच्छा मुझे तो लगा था कि वो कोई भी एक्सेस कर सकता है एक सेकंड फिर 1 second let me see I can share that with you because प्रेजेंटेशन बाद में रेफर करने का जरूरत पड़े तो
मैम एक चीज आपसे जैसे कि मैम हम लोग का ये तो मैम 48 वीक का कोर्स है।
हाँ हाँ कितने
हम
वीक
लोग
का
8 वीक 2 महीने का है ना?
12 का नहीं है ये तो 12 वीक्स का है
सॉरी मैम तो मैम हम लोग मैम यस मैम तो मैम मैं ये पूछ रहा था कि मैम हम लोग उसमें भी मैम सेट 1 सेट 2 सेट 3 तो मैम हम लोग का ये सेट 3 या सेट 2 कोर्स है मैम।
तुम्हारा वॉइस बहुत ब्रेक हो रहा है फिर से बोलो
मैम हम लोग का ये 3 मंथ्स का कोर्स है
हम्म
ना वो सेट में डिवाइडेड है मैम सेट ए का होगा मैम शायद 1 महीने का सेट 2 तो हम लोग का ये अंडर सेट 3 है ना मैम।
ये तो मुझे नहीं पता ये मुझे मतलब मुझे ये सेट ए सेट बी सी का पता नहीं
ओके
बट मैं एक काम करती हूँ मैं यहाँ पे दिस आई एम पुटिंग दिस लिंक हियर सी इफ यू कैन एक्सेस इट तो उसमें मैं मेरे मतलब इंडिटरमिनेट सॉल्विंग का जो स्लाइड्स है ना उसमें एग्जांपल्स होंगे वो मैं अपलोड कर दूंगी फिर ओके
हाँ मैम एक्सेस तो कर पा रहा हूँ।
ठीक है, तो यहाँ पे प्रेजेंटेशंस दिख रहे हैं ना? तो मैं
हाँ
अभी
मैम।
अभी सिर्फ 3 वीक का है। मैं इसके बाद सारे सारे वीक्स का डाल देती हूँ यहाँ पे। तो वीक्स, तो जिस जिस वीक में वो इंडिटरमिनेट स्ट्रक्चर्स का सॉल्यूशन है, वीक आई थिंक 7 8 9, वो वाला एक बार देख लेना, उसमें एग्जांपल्स होंगे तो ये समझ आ जाएगा।
ठीक है मैम।
ओके।
थैंक यू।
ओके।
मैम वैसे मतलब मैम आउटसाइड का,
हाँ।
मतलब जैसे आप पढ़ा रही है तो उसमें तो डाउट वैसे होता नहीं मैम, आप बहुत अच्छे से बता देती है, लेकिन आउटसाइड का बहुत सारे क्वेश्चन है मैम, तो वो आपको मैं मेल पे भेजता नहीं मैम, क्योंकि अगर आप बोलेंगे कि वो तो कोर्स से रिलेटेड नहीं है, तुम बाहर का लेके आए।
कोर्स से रिलेटेड नहीं है मतलब वो स्ट्रक्चर एनालिसिस ही नहीं है क्या?
स्ट्रक्चर एनालिसिस का है लेकिन, बट वो मैम मेरे कॉलेज का प्रॉब्लम है, या फिर मैं सॉल्व कर रहा हूँ मैम।
मतलब वो बात का है, मतलब इट्स अबाउट, मतलब बात के टॉपिक्स के है। हाँ, तुम मुझे ना एक ही थ्रेड में भेजते रहना। आई विल की ट्राई टू सॉल्व दिस। एज आई सेड, मुझे थोड़ा सा रिवाइज करना है बात के टॉपिक्स, क्योंकि बहुत साल पहले पढ़ा है मैंने ये सब। लेकिन आई विल, मतलब इवेंचुअली विल गेट देयर, एंड बिफोर दैट आई विल ट्राई टू सॉल्व। तुम एक ही थ्रेड पे भेजना, ठीक है? इसी अभी जो क्वेश्चन भेजे हो, इसी पे भेजना।
ठीक है मैम। थैंक यू।
हाँ, ओके। I'll upload the all the PDFs, all the presentations by tonight. Okay. Are there any more questions?
मैम।
Okay, then I'll end the class. We'll meet again next Tuesday.